Morning and welcome to Physics 3. Today is April 28th. So we are coming to the end of this class. We still have basically about a chapter left and some change to finish the entire thing. The last lab that we're going to go through today, I'm hoping that you guys will not have difficulty with it. It's mainly simulations using Excel, actually. And the questions, you guys should be able to also answer them. So we're going to go through that. There was actually a mistake last time when I was talking, and sometimes when you get to talk and you don't think, you make stupid mistakes. And about the weak nuclear force, basically bosons, and I mentioned W plus minus 0. Actually, the W plus and the W minus are correct. The 0 charge is actually called the Z boson. So we're going to come to them. We're going to talk about this stuff in chapter 44. So this is something that that I mentioned last time, and immediately after class, I just realized that basically I didn't think through what I was talking. Anyway, we still have a few items from chapter 43. We still have chapter 44. Chapter 44, in terms of the approach we're going to take, it is mainly descriptive because we really don't have enough mathematics to talk about the stuff that we need to do. But that should not prevent us from doing some calculations, especially when it comes to cosmology. So we'll come up with some estimates for the critical mass for the universe, critical density for the universe, that the universe must have in order for it to either continue expanding or collapse on itself, or basically marginally go about it. So we'll do that. We'll also do some basic calculations using the Heisenberg uncertainty principle to determine, among other things, the different epochs of the universe and how it went through from the early time immediately after it was, after the Big Bang, and then the different stages it went through up to the current era that we are in right now, which is the age of the stars and the galaxies. So that's basically the stuff that we're going to explore from chapter 44. And with that, basically, we'll finish. Then we still have to meet. I know some of you and a lot of you are not present right now. I have about 1/3 of the class right now, so 2/3 of you are basically planning to watch this one recorded. We still have to meet after chapter 44 to go through the review process for the last exam, exam 3, that is, in terms of materials that are going to be covered in terms of practice problems, because if you guys noticed, we are not doing as much problems. I don't know if we did from chapter 41 at all, or we may have done something, but for sure chapter 42 and now chapter 43 and 44, we're going to combine that into one session where we go through each and every one of them to see a list of problems that I will give you, basically, so that you guys can work out. And also we'll do some of them in class so that we can have an idea on how to tackle those problems. So we need that at least another period, maybe 2 of them, 2 sessions to finish this. And then also, of course, we still have our exam 3, and we still have our final, and we still have our post test. And that's basically everything that we still have in terms of assignments. Okay. So let me share the screen with you. Share. So last time we were talking about the beta decay and the alpha decay and the gamma decay, basically radioactivity, and we came up with this law that basically tells us that the rate at which this decays are happening is proportional to the initial mass. So this is some sort of a semi-empirical law, if you wish to. where lambda here is a characteristic of that decay. And this is a simple enough differential equation that you should be able to find just by finding the natural log and taking the exponential. So that's basically the solution, the initial conditions, and basically you have the solution. Then we define the half-life is when half of my material is gone. When that is, that's going to give me T1 half is basically proportional, inversely proportional to lambda. Which is characteristic of the material, and then you have the natural log. Then the T mean or the lifetime is just the inverse of the log and the inverse of lambda. So it's related to 3.5 by that natural log. And also we talked about the different kinds of decays, the alpha decay, the beta decay, and the gamma decay, and how much penetrations each and every one of them has, namely the fact that the least penetrating one of them is the alpha particles because they are massive, actually they're supermassive compared to the other particles. And then we have the beta decay. It turns out that there are at least 2 kinds of beta decay. There are 3 of them to be more specific. There is the beta minus decay, where there is a negative charge is basically emitted in this case, an electron is emitted. And then the beta positive or the positive beta decay, the positive beta decay will have a positron basically emitted instead. And you also have the electron capture, which is also a beta decay also. And then the last one was the gamma emission, which is an unstable element just to rearrange itself because of the shell model, basically, that we discussed before for the different forces as they're interacting inside the nucleus, basically, so that the nucleus rearrange itself to minimize its energy, goes from an excited state to a lower state by emitting a high energy frequency, which is the gamma rays. So these are the different stuff that we talked about. We talked about also the basically the gamma model itself for the nucleus, and we came up with this expression in here where the C1, C2, C3, C4, C5 are scaling factors. They are actually of extreme importance. In this case, they are actually determined by experiment, okay? And you have the values given for you guys, how much they were. And the last term in here, we made a big fuss over it, that sometimes it's 0, sometimes it's positive when the number of nucleons, basically both the protons and the neutrons, they're even, and it's negative when both of them are odd, with the exception of few elements that are stable in nature, and there are 4 of them. The rest of them need to really have the number to be either even, all of them even, or some of them are even. When there's some of them, when the neutrons or the protons are even and the others are not, then in this case, I just use 0. So this term does not contribute at the end. So we have an understanding of what this expression is coming from. This is the volume, volume contribution, basically the fact that you have the nucleons are connecting to one another from every which way. So the binding force in this case is its max. But then the surface tension in this case tries to basically break that structure apart a little bit. Hence you have the minus sign. The positrons and the protons in this case inside the nucleus, they repel each other. Therefore, they basically contribute. They try to diminish from that binding energy to make the entire nucleus unstable. And this explains the fact that we don't have large nuclei. I mean, at some point after Z equal to 92, this number and A more than 200, then in this case, this atom becomes unstable. So this term now plays an important role. And we're going to talk about this one in there, okay? We're going to go in detail about this one. And then we have this discrepancy between the protons and neutrons, and that is to satisfy this NZ model, NZ graph model. So basically, observation shows that for the most part, this is first of all, the N equals to Z line. I tried to graph this in such a way that all of the number of neutrons is always higher than the number of protons, with the exception of 2 elements. The first element is the normal hydrogen. For hydrogen, you have really 1 proton and 0 neutron, okay? So in this case, the number of protons is 1, the number of neutrons is 0. So that is an element where you have the number of neutrons is less than the number of protons. So this curve really starts from here. It doesn't start from 0, 0. It starts from 1, 0. Okay. So the y-axis is 0, 1, the number of protons starts 1. So that is the starting point. So this is the first element. The other element that is known in nature, and that's the only one, is actually helium 3, the isotope of helium. So that is the only element also besides hydrogen, because the other deuterium is actually have 1, 1. So it's on the curve right there, okay? The heavier, the triton, which is also another isotope of hydrogen, has actually 2 neutrons and 1 proton. So it's above the curve. So we don't care about those 2. The other element in nature where the number of protons is less than the number of neutrons, the number of protons is more than the number of neutrons, and that is helium 3. That is actually a stable element too. And those are the only 2. You have the normal hydrogen, okay, and isotope helium 3 of the isotope of helium, where you have 2 protons and 1 neutron. That is it, no more, okay? So everything else is above the axis. What we noted is when that difference between the number of protons and number of neutrons starts to be different, then in this case, the element becomes unstable and decays using beta decay to go into the configuration basically where N and Z are very close from each other. As you can clearly see, when the atomic mass grows, when Z grows, there is a difference. More neutrons are present than protons. And you need that to, if you wish, glue those protons together because they tend to repel each other. So you need them to be slightly more to help in the binding, but not too much, because too much becomes the unstable, and then the whole thing goes back into a more stable configuration. As a matter of fact, when you have too many of them, then the particle in this case, when A becomes more than 200, then the nucleus goes radioactive, and in that case, most of the time it's an alpha decay, and that alpha decay basically turns the element into a more stable element. So let me mention 2 things from last time that I didn't go in detail about, but they're important. The first one is the different types of beta decays. And the neutrino hypothesis. I mentioned it briefly last time, but we really need to understand what's going on in there because it's relevant to chapter 44 actually. And then the other question is the alpha decay. And this was part of actually an exam 2 that we had last time. Okay, for the alpha decay, as I was saying, when the nucleus becomes too big, when A is bigger than, let's say, for example, 210, okay, or 200, okay. In this case, the distance. Remember, the radius of the nucleus in this case is still given by R0 times A to the power 1/3. So this number in this case becomes, the radius becomes too big. As a matter of fact, this radius becomes the cubic root of 200 is what, 210, which number I should multiply it by itself to get 210. That should be what? 10 times 10 times 10, that's a lot. So that's not, I'm sorry, what am I talking about in here? So what is the cubic root of 210? Let me do it quickly in here. It's about 6, okay? So this is about 5.9. It's about 6 R0, okay? So now, I mentioned last time that the nuclear force, the strong nuclear force is at its best around 1 femtometer. When you go about 3 femtometers, at that point, the nuclear force drops and drops practically quickly, okay? This is distance that is 6 R0, which is about 6 femtometers. At that point, the nuclear force is so weak that it's dominated in this case. So what dominates the force is actually the repulsion, the Coulomb force. So in this case, it dominates at this sizes. So when you have atomic masses of the order of 210, at that point, the nucleus is really not stable inside. It's really wants to decay. Most of the times, in this case, it decays into an alpha particle by emitting, basically getting rid of those extra 4 nucleons at once. So basically getting rid of 4 nucleons. So this number drops by 4. And it's going to continue until most of the time it ends up in lead, but that's something that that is part of the process in this case. So it's going to go through a series of beta and alpha decays until it gets into a stable configuration. So in this case, when the number A is large, you're talking about distances of the order of 5, 6 femtometers. So at that point, the nuclear force has dropped practically to 0, and the Coulomb force now overtakes the whole thing. Neutrons, they can't help in this case with the Coulomb force because they don't have a charge. So in this case, the protons start to basically, the ones that are far apart. You still have protons that are close from each other, and those they are helping in the binding because of the nuclear force. But the ones that are far on the far edges of the nucleus, in that case, they basically start to repel each other, and the whole nucleus becomes unstable. So in terms of a model, this is how it looks like. We're going to represent it. So this is the energy, and this is the distance, okay? And this is the energy, the potential energy, okay? Well, up to a certain point, I'm going to approximate it. I know the book gave you a little bit of a curve that is a little, but if you do calculations, you're going to approximate it to a square well. It's much easier to do the calculations, and that's how most of the, how we can do this, okay? So what is my pen in here? Okay, here it is. So it's going to be roughly the binding energy on average of the nucleus in this case. So it's a negative energy. So you need a negative energy to have the nucleons basically stuck inside the nucleus. So it's a negative energy in this case, okay? And then up to a certain point, I'm going to drop this nuclear force to 0. Obviously, this force is not exactly the nuclear force, it's adjusted a little bit, okay? So at some point in here, which I'm going to approximate to about 5 or 6 femtometers, okay? This depends on the species though. This depends on which nucleus we're talking about. This depends on which A we're talking about. So this distance and even you not. But I'm trying to give a model, theoretical model. And after that, we have the Coulomb force. Well, the Coulomb force is, in this case, a positive force. It's a, I mean, the potential energy in this case is positive. It's trying to break down the whole thing. So in this case, the nuclear force, and it's going to drop with 1 over R, okay? Remember, the potential in this case is just charge times charge, which is E squared divided by 4 pi epsilon naught, depending on how many, again, depending on the species, depending on Z, and that's going to have a distance in the denominator. So the distance, again, drops like 1 over R. Obviously, this is the properties of the, so this is the potential basically that we have. Here is the observation though. And that's something that is related to the exam too. The alpha particle, when it emerges in here, it's going to, let's say, for example, this is on average, it's anywhere between 25 to about 30 or 35 mega electron volts, okay? So this is depending again on which element we're talking about. But the alpha particle will have a range of kinetic energy that it emerges with about basically 5 to about 10 mega electron volts. So how come an alpha particle that is sitting in the nucleus in this approach make it to the other side, basically of the outside of the nucleus? And again, this is something that we saw in exam 2, and it has to do with the quantum tunneling. That's because there is a barrier in here that it needs to overcome, and it doesn't have enough kinetic energy to overcome it. It's like me, for example, taking an object like this one and throwing it and expecting it to have enough, I mean, with a velocity that is less than the escape velocity of the Earth, and expect it to be in orbit or to expect it to even leave the Earth in here. to escape from the Earth. That is not possible. By the way, the escape velocity was determined by when you equate the potential energy to the gravity with the kinetic energy of the escaping particle, and in that case, you find the escape velocity. So if I don't have enough kinetic energy, I will not be able to escape the pull of the Earth, because we have a gravitational pull that is given by the basically the 1/r also law. So in the same fashion, in this case, the alpha particle really does not have enough kinetic energy, according to the classical model, to basically leave the nucleus, even in this situation. Remember, the alpha particle is represented by a wave, and that wave, in this case, is going to decay exponentially, where this function, wave function in here, will be continuous at the boundaries. This is how we came up with the approach in here. We impose the continuity of the wave function itself and its derivative, because the Schrödinger's equation of the second order. So when we solved it, we saw that it has a tail in here, and that tail at the end will give me a non-vanishing probability that the wave function will tunnel to the other side. And if you guys remember that the tunneling probability is proportional, so there is that G factor, is proportional to exponential of -2 kappa times L, where L is this distance. So this is L, is the width of the barrier, okay? Obviously, kappa, we saw it also, and some of you probably made that mistake. I hope that you fixed that. It's equal to 2m times the gap in the energy between this and that, which is, let's call it U, minus E, divided by h bar squared. I mean, you can take the h bar squared outside, but that's another thing in here. And m is the mass of the alpha particle, okay? So we have that, and this term in here, as you can clearly see, if L is big, the exponential is small. If L is big, the exponential is small. So the wider the width in here that I end up with, the less probable that the alpha particle will make it out of the well. And also, the smaller the gap, in other words, for another species, for another alpha decay, I could end up with a particle, for example, that is, let's say, for example, this was really 4 mega electron volts. So the gap in here, and let's say this one is, for the sake of argument, is 25 mega electron volts for my case. Obviously, 25 minus 4 in this case is going to be 21. But if I end up with another one that is sitting in here, let's say, for example, it's 10 mega electron volt. Obviously, the gap in here is less. It's only 15 mega electron volt. And L itself is a lot less too. So this number is less, and L is less. So this probability will be higher because you have an exponential of negative in it. So it's going to tunnel easier, and brings me to another point, which is called the Geiger-Nuttall law, which is as follows. Obviously, this one will have higher energy and less gap to travel through, so it's going to make it, by just keep on hitting on that wall of the nucleus, it's going to make it easier to the other end. Whereas this one really has less probability, so it's going to hit a lot. So you have so many attempts before it really escapes, tunnels through to the other side. So this decays more rapidly. This species will decay more rapidly. In other words, it will have a T1/2, which is shorter than the T1/2 of this one. The half-life of this one will be shorter than this one. Furthermore, this will be more energetic when it comes out. It's going to be at around 10 mega electron volts than this one. So this one will have a higher penetration. So in other words, if you see how far it's going to go, and you put several sheets of paper and you try to detect the alpha particle on the other side, this one, you will need a lot of them to slow it down or stop it completely, whereas this one, you really cannot. You have to have only a handful of sheets of paper before the alpha particle is actually gone, because it did not have enough kinetic energy to continue through. Do you guys understand the physics of it? So this is what the Geiger-Nuttall basically law says, that the half-life in here depends on this gap, really. And the penetration also depends on that gap. So if you look at materials, there is different lifetime for them, different half-lives for them. Some of them live for a few seconds. Some of them actually would last for a long time before they decay, okay? So, and that has to do with this gap in the energy. This is called the George Gamow, I mean, it's the same guy, so it's not two people, model. Okay, this, as I was saying, it was part of exam 2 because it was related to really chapter 41, was it? No, chapter 40, when we did the calculations in there for tunneling in 1D, and the same formula actually that we find in 1D and using it in here in 3D. Okay, so that's basically the same thing in here. So this is basically the idea behind it. Does this make sense to you guys?
Yes.
Okay, very good. So this is basically some of the stuff that has to do with the alpha decay and some of the observations that people did. And remember, this is started a long time ago in the 1911 when this law was discovered. And then the model for it, when Mr. George Gamow came up with this model, explains exactly the observations that this higher energy particles, meaning they have a higher penetration in hearing gap, they have short half-life, whereas the low energy ones, meaning that you have a shorter penetration depth than the others, then in this case, they seem to have a half-life that is less. I mean, longer. I'm sorry, longer. T1 half is proportional to, or inversely proportional to the penetration depth. Do I have it correct in here? They have a penetration depth that is short. No, it's proportional. Yeah, it's proportional. Directly proportional. Okay, so if the penetration depth is, no, it's inversely. What am I talking about? So if the penetration depth is large, that means T half is T half is small. That's basically what that is. Okay, so exactly explained in here. So this is an observation based on experimentation, and this is something that the model that explains it, and it fits perfectly using this expression here. It fits perfectly the bill. Okay, so this is one thing. The other thing that I want to talk about is the beta decay, which is also part of the discussions that we had last time. So in the beta decay, as I mentioned before, you have 3 types. You have basically, it boils down to, you have different elements that go from different properties. So the neutron has no charge, and it's baryon number of 1, or it's neutron, decays into a proton, which is 1, 1 in this case, plus, in this case, you're going to end up with, because this is a positive charge, you're going to end up with a clearly an electron. So this is basically what was observed, okay? You have different kinds of materials emitting an electron in changing their species by changing Z to Z plus 1. Okay, so whatever Z was. So you have an element in here that was of a Z value and an atomic mass A. So all of a sudden, it keeps its mass, it doesn't change, but Z increases by 1 by emitting an electron. So we know this process. Another type of beta decay, you have an element, in this case, with a Z number and atomic mass A. So in this case, it's going to retain again its mass. Always the mass doesn't change, but Z decreases by 1 by, in this case, emitting a positron. So these are the beta decays that you had before. There was a problem though, and the problem has to do with the kinetic energy of the electron in this case, because it's very easy to find it, how much energy it's going to have. You know the mass of the neutron, you know the mass of the first element, the mass of the second element, you know the mass of the electron. You just find the difference in masses, and you should find the kinetic energy in this case with which the electron is supposed to have. And this should be specific value. This should not really be something that changes. This should be a fixed value, okay? And as a matter of fact, if you do the calculations for a lot of observations, so this is the probability. And your expected value in this case, so this is the kinetic energy of the electron that is emitted, or a positron that is emitted. So in this case, this is a value that you're expecting. You could expect something that is due to the error around it fluctuating because you're doing this experiment time and time again. But this is what was noted, that the kinetic energy, the kinetic energy has a probability distribution that look like this. As a matter of fact, this value, that your expected value, is not coming up. It's at the end, the tail of it. It peaks somewhere in here. But you have the whole spectrum covered. So what's going on in here? It seems like this one violates, both of them violate the conservation of energy. That was a problem. The energy is not conserved for some reason. For a specific experiment, it doesn't matter which. Let's say, for example, this is how much you ended up with. This is the kinetic energy that is measured, because this is a bunch of measurements in here. So what happened to this energy in here that you have? Where did it go? So this is the kinetic energy of the electron that you really ended up with in that specific experiment. So where did the energy go? So that was a question that people were struggling with. Okay, that was this problem. The other problem also is the momentum. If you take a specific element in here, and a typical example, textbook example, is the boron going into a decay and giving you carbon. In this case, remember, Z changes 12. Okay, plus in this case you have an electron that is emitted. Okay, so this is a beta decay, beta negative decay. So if you take a boron in this case, this isotope of boron, and it's going to decay into a carbon. So you have the carbon atom, for example, recoiling in a direction. Let's call it the X direction. It doesn't matter which. And the electron in this case comes out in this direction. So this is clearly a violation of the momentum also. Momentum is not conserved. And that's a problem. These are one of the two most known physical laws in nature that are true in classical mechanics and relativity, and also up to this point true also in quantum mechanics. And they have solid arguments based on symmetries that they should be true all the time. Okay, so those are two big laws. The third violation, so their nightmare did not end for physicists there, and they were faced with tremendous problem, is the spin. Let me explain what's going on. Let's go back into the actual interpretation of what's going on in here. So this is a spin 1/2 particle. This is actually a fermion. This too is a fermion. This is also a spin 1/2 particle. So if this one was pointing up, for example, this has two possibilities: is to go there up or down. That's fine. You can explain basically by accounting for the other spin 1/2 particle. But then you have a problem. If this was up, and this you take it up, then where did this go? If it goes up, now I have two up particles. So the angular momentum is not conserved. If this goes down, then they cancel each other. And I had a spin up to begin with, an angular momentum pointing in one direction. Now I don't have any. So the angular momentum also, the spin is not conserved. So the newly basically emerging property that seems to be conserved every which way also, and that's the angular momentum, which is also has powerful arguments from symmetry and all of that, is also not conserved. So this is really a problem. This has really presented itself as a major problem in physics. Big names in physics. Niels Bohr himself basically suggested that, wait a minute, maybe these things are not conserved. Energy, momentum, and angular momentum are not, beta decay does not conserve them. So, because this is what the observations are showing us. Okay, so that's the problem we were faced with in the beginning of the 20th century. It was actually, what is it? Pauli, I think, is the one who objected on this. And he says, no matter what, these things must also be conserved. And the rationale for them are basically outside of the scope of this. They have to do with symmetries. So if symmetries are violated, then we really have to address them, why they are. This is the symmetry in time, this is the symmetry in space, and this is the symmetry due to rotations. So where is that thing coming from? So we really have to fix this. So he suggested maybe we're missing a particle in here. Okay. And that particle will account for this missing energy because it will have a mass, so that adds to the energy, and it will also have a, I mean, if it has a mass, if it's a massless like the photon, then it's another problem. But at least in terms of energy, it will carry with it that energy to come up with a difference in here. That's basically his thinking. Immediately after that, Fermi picked up the point in here and tried to come up with a hypothesis for this particle. First of all, in terms of charge, this beta decay conserved charge. I started with 0 charge in here. For this case, I ended up with 0 charge because this is a +1 plus electron, and this is a minus plus 1.6, and this is a minus 1.6, so they cancel each other. So the charge is conserved. The same thing with the beta plus also decay. I mean, the other type of decay, where you have actually a proton going into a neutron plus a positron. So the charge in here was +1. Now it's still +1, so we're good because the neutron does not have any charge. So the charge is 0. So in this case, this particle, if we're going to add it, better have 0 charge. So the first condition on it is 0 charge. So it's neutral. The second condition of it, it has to do with the spin. It must account for the other spin. Basically, if this is spin 1/2, this is spin 1/2, this is up, this is down. So I must have another up in here so that I have 2 ups and 1 down to account for the up. If this was down, then it still has to account for, if this is down, the other one has to be up. In other words, I have to have a spin 1/2 in here. So this particle in here must have a spin 1/2. So it's really a fermion. It's not like a boson, okay? So that's one thing. So most likely it has mass now, since it's a fermion, because all fermions have masses. So it's not like a proton, although in the case of the W plus and minus and the Z bosons, they actually have masses too. But it really is an indication in here that it might have a mass, and we'll talk about that mass shortly. But before I do that, if we have this particle now, it's going to fix this problem, because if that particle is flying in here, then I have conservation of angular momentum now. I mean, of regular momentum, because now I can do my vectors and I'm in good shape. It also solves this problem. Now, the mass that it has, because remember, the electron is tiny. It has a very, very small mass. It's 0.5 mega electron volt. And we're talking about its kinetic energy being split into its own kinetic energy, the amount of energy that it should have, its kinetic energy, plus a change in mass, plus. So this is probably the mass is somewhere in here of this particle, plus its kinetic energy to account for the difference. So its mass must be smaller than that of the electron. Small mass compared to that of the electron. Okay, so it's a very, very small mass. At this point, we really don't know exactly how much mass this particle is. So he called it, so it fixes the energy problem, it fixes the momentum problem, it fixes the angular momentum problem, and it fixes everything else in this case. So he called it the neutrino That's what Mr. Fermi has called it, the neutrino, which really stands for the little neutral one. Okay, that's exactly what the name is. Obviously, that was suggested in 1930s, 1932 or 33, and then it was discovered about 20, 30 years later, actually, around 1960, when it was actually discovered. Here is how we can discover it, because there is a problem. It has a little mass to begin with. So in terms of a gravity, forget about gravity all the time when you're dealing with elementary particles, because of the fact that they don't have enough mass. So gravity does not come into play at all in here. So forget about gravity. It does not have a charge, so it's not going to interact with the protons or electrons as they go along electrostatically. So it has no interactions with those. It also does not interact with the nuclear force, the strong nuclear force. The only way that this particle interacts with is through a radioactive decay. So this particle only comes into play with the beta decay only. So this particle in here, which we give it the symbol nu for the electron in here, is this one. There is another problem that needed to be fixed, okay? And that is because of the spin. Whatever the spin of the electron, this particle must have the opposite spin to it. So that's really how it boils down to it. So it's really for the case of the electron, we have to have not the neutrino, the regular neutrino, we really have to pull another antiparticle to it, which is the antineutrino, just to account for this two to cancel each other, just from this observation. There is another reason that we're going to see in chapter 44, why you really need an antineutrino for the electron, and you need the regular neutrino for the case of the positron, because the positron itself is actually the anti-electron, the anti-particle of the electron. So because of that, then you need the opposite to what you need for the electron. So whenever you see a beta minus decay, that beta minus decay has the antineutrino in it. Whenever you see a beta plus decay, that means you have actually a neutrino to it. Okay, so that clarifies all of the properties. So it must be, and it must have also all of the properties needed to fix all of the problems. The other reason why actually this is actually more sound, and it's coming from chapter 44, and that has to do with something called the lepton numbers, okay? So this has a lepton number of 1 for the electron. This must have a lepton number of -1. So just to compensate so that there is no change in that number. So again, it's coming from chapter 44. But the point being in here, we have a full hypothesis for it that was discovered later. So how are we going to discover that? That's the question. And it's a very important question. The only way to discover it is by knowing what is known as the inverse beta decay. So the beta decays are basically, as we described it like last time, are the beta minus, which is the normal one. So in this case, you have a neutron going into a proton, plus a normal electron, plus in this case, an antineutrino of the type electron. And the beta plus, where you have in this case a proton going into a neutron, plus a positron, plus in this case a regular neutrino. There is another one that looks like the opposite of this one, which is the captor, which was also it's a beta decay called electron captor. This also happens in nature a lot. So you have one proton, add to it a normal electron. In this case, you end up with a neutrino plus a neutron and a neutrino, a regular neutrino. The electron captor in here is really what is responsible for the formation of neutron stars. That's really, the main process. In regular matter, when the number of protons is more than what it should be in a nucleus, it becomes unstable. And all of this is coming, by the way, from the model that I described early on last time. For the shell model, basically, one of those protons and one of those neutrons changes shape to become, so in this case, I have excess protons. One of them is sitting in here, and I have room in here available for it for the neutrons. So this proton will change into a neutron and give me a neutrino. By capturing the lowest level electron in the electronic structure, so it grabs it basically into the nucleus and makes it into the nucleus. At that point, it becomes a neutron. So the species of the atom basically changes. The chemical properties change completely in this case because you lost one of them. So the Z moves in the opposite direction. And in that case, you emit a neutrino, and the nucleus becomes more stable. Okay, obviously, now you have a K shell that is missing an electron. So electrons from higher energy levels will jump to replace it. So now the atom basically is an excited state too. The entire atom, I don't mean the nucleus. So in this case, it's going to emit X-rays too. So in addition to that, so because you have the transition to the K shell, which is the lowest energy level in the atom. So in this case, also that process comes into play. So that's something else in here. So this is the electron capture. In the case of the neutron stars, not only one of them, but a bunch of them come raining down on the nucleus, basically, and you will form as many neutrons as possible out of the protons that you have in the nucleus. Until if you have a lot of gravity, in this case, all of them will change. So this is basically the different types of decays. Now, I was talking about the reverse or the inverse beta decay. And the inverse beta decay is if you take, because this one suggests it immediately, okay? If you take this one in this case, you have a neutron. It captures a neutrino, normal neutrino, and gives you a proton and an electron. So if you have a neutrino that is fast enough, it could be captured by a neutron and changing the species again by increasing the number of Z, and plus an electron that is emitted in this case. Well, this is the process that we use actually to detect the other reverse process involves actually the antineutrino. And the reason why I'm talking about this process in here, so there's another inverse one that actually involves the capture of an antineutrino. So in that case, you have a proton that captures an antineutrino and goes into a neutron plus a positron. So it's the inverse of this one. So this is the inverse of that. And the first one is the inverse of, I'm sorry. Yeah, it's the inverse of the beta positive, and the first one is a beta negative one. So the point being in here is, how do we detect these neutrinos to begin with? By using the inverse beta decay. So imagine you have sensors that are susceptible to this capture of the neutrino. So if you have one capture, and then in this case, the detector will specifically see the change in the species that you have in there. And at that time, the light bulb will go on. So if you look at the Kamiokande, basically detector in Japan, and the one in Canada, and all the ones that are now popping up, they use this method to detect this, because the only way for a neutrino to be actually detected is by interacting via the weak force, and this is the weak force. Okay, that is the only way for us to detect them. So again, we went into a little bit more details into how these processes work. And the reason why this discussion is important because of the fact that we still have to talk about the nuclear reactions. And since I'm talking about the nuclear reactions, let me start with the sun. Okay, the sun goes through a proton-proton chain. Okay, so what you have in that case, in the case of the sun, you have the temperature inside the sun is about 15 million Kelvin, about 1.5 times 10 to the power 7 Kelvin. This is a very high temperature, but it's really not high enough because a lot of these protons, as they come in with, you remember, their distribution is given by the Maxwell-Boltzmann distribution. So in this case, some of them are very slow and they approach each other. So they repel each other because of both of them have a positive charge. And that is the proton in this case is really hydrogen. Okay, ionized hydrogen. So in this case, they will repel each other. And in that case, nothing happens. But some of them are moving fast enough with the same Maxwell distributions that they get close from each other to about 1 femtometer. This is a very, very rare, and you will have problems to do this one, a very rare probability that it doesn't really happen that often. Because if it was not that rare, if it was more dominant, if it happens a lot, the sun would have run out of protons a long time ago, basically, and did not have enough time for basically run out of energy and would not have allowed the evolution of the solar system the way it is right now. Like, for example, life on Earth, it would not have sustained that much heat. So the probability is extremely rare, so that it doesn't happen that much to the point that the sun basically takes a long time for it to continue fusing those hydrogen atoms. So that's one thing. The probability also is not too fast either. I mean, is not too slow either, because if it's lower than what it is right now, the sun would not have had a chance to, because this probability will be extremely low, that in that case will not have generated enough energy to basically dissipate it in all the time. So it has really a very small probability of the order of 10 to the negative 26 or something, but just the right number for it to continue living for about 10 billion years. So this is basically the process. So at some point, these two, they will be close from each other. Now you have two protons that are extremely next to one another. And I was describing the model, the shell model. One of them has to switch using the beta decay. One of these two protons has to go into a neutron using this process. So one of these protons goes through a beta plus decay and becomes a neutron, emitting a positron and a neutrino. So the outcome then in this case is going to be a heavy hydrogen, because this is how the structure would look like now. You have a proton and you have a neutron. So this has two nucleons, plus of course the positron, plus of course the neutrino. Well, the positron is going to be annihilated immediately after it forms. It's going to encounter another electron, because you still have those. There, remember, hydrogen is ionized, so you still have a lot of electrons floating. So it's going to be captured by an electron, and then this process will emit two gamma rays. The reason why you really need two is because of the conservation of momentum. So in this case, it's going to be annihilated, and you can calculate how much energy is that. That's not a big deal. I mean, you can 0.55 mega electron volts. That is the energy of each gamma ray, really. Okay, and that's a very high energetic frequency. Okay, so plus the neutrino. Now you have a proton now that is sitting in there. I mean, not a proton. That you have a deuterium now. So this is no more. So this is the stable version of hydrogen. It's going to capture another proton and change to a helium-3 now. Plus, of course, gamma rays too. Okay. So there is 3 ways of forming gamma rays in here. But helium-3 now, imagine you have a parallel process also that happened in the sun that generated the helium-3 also. So you end up with another helium-3 in here. So basically this whole process times 2, okay? So this whole process times 2. So in this case, you will end up with 2 helium-3 combining, fusing, and forming a helium-4, normal helium, plus 2 protons. So this is basically the outcome at the end. So how many protons did we end up with? Did we start with? We have 1, we have 2, we have 3. But there is a parallel process also that adds up 3. So for a total of 6 protons come into the equation. 6 protons at the end, you're left with 2 that are basically thrown back into the mix. So 2 are going to go back. So a net in this case is 4 protons come into the process. So 4 protons plus the outcome is a helium atom, basically a helium nucleus, okay? Alpha particle that is coming out of the process. Now, don't forget the energy that is coming. You have 2 gamma and 2 gamma plus another 3 gamma on the other side. So there is plenty of energy. These gamma rays are extremely highly energetic. That's not what we see right now if we go outside. The light that is coming from the sun is for the most part in the visible range. So again, we did the Compton scattering, and that was one of the problems we discussed, is that the gamma rays, they go through a lot of scattering inside the core of the sun, so that the wavelength lengthen until they reach in the visible range. By the time they emerge from the photosphere of the sun, at that point they are in the visible range. So we can see them. So again, takes a long time. That process takes about 100,000 years or so for that gamma ray to emerge from the sun. But now, the other also outcome of it is that you have 1 neutrino coming from this side, and you have another neutrino coming from the other side. So you have 2 neutrinos. So the outcome then, the summary of the process is that you have basically 4 protons mixing together, giving you a helium in this case, plus 2 neutrinos, plus gamma rays, plus energy. That is the net equation. Obviously, the process is not just one. It's not like 4 protons mixing together at once, and all of a sudden you have that. No, okay? You have stages in between that involve positrons, and those positrons, they get canceled. And you also have helium-3 that forms in the mix, and you have also deuterium that forms in the mix, and so on and so forth. So by the time we reach this stage, this is basically the outcome. Well, here is the thing. If something happens to the sun today inside the core of it, is there a nuclear reaction, for example, increases or decreases? We wouldn't tell. We can't tell just by looking at the energy that is emitted, because the photons that are coming now, they have actually started their journey about 100,000 years ago. So if something happens today to the core of the sun, we wouldn't know. Did the rate of the nuclear reaction increase, decrease, something happened to them? So we wouldn't tell. We'll have to wait that long really to tell that something happened. The solution, though, is those neutrinos. You have about 10 to the power 58 based on the mass of the sun, based on the estimates for the core. This is how much mass you should have. Okay, so you can come up with an accurate number for them. So those, they don't interact, remember, with anything. They come out straight out, okay? With the way that I was describing them, with these properties. Extremely small mass, so they're not going to collide with anything. They're going to go straight through. As a matter of fact, you're sitting right now and you're being basically you're drowning in them. They're coming from every which way, okay? So there is photons everywhere and your body doesn't interact. No matter basically interacts with them for the most part, okay? You have to really have special equipment that is buried under the ground to really detect one in a long, long time, okay? So you really have to wait for a long time before you start detecting one or few of them here and there. Even you have the equipment for it. They have no charge, so they don't interact electrostatically, so they come unimpeded. And they don't interact with the protons or neutrons for the most part, so they come out unimpeded. So you can find an estimate based on the number of protons and neutrons inside the sun. You can find with a good estimate how much Earth should receive. Here is a problem, though. When we use those detectors, as I was saying, we didn't find the number that we should have. We found the number to be about 33% of what they should be. okay? And that presented a problem. For a long, long time, people were either we have the wrong picture of what's going on in the sun, or we are not doing a good job at detecting them because we're missing about 67% of them. So where is the missing part is gone? So that was part of the problem in studying the sun, because those are the messengers that are coming from the sun unimpeded. It takes about 8 minutes for them. They travel with almost the speed of light, so they come straight through. So we should be able to detect them, and we detect them, all of them, but we're detecting only about a third of them. Until the experiment was, we learned about another property that the neutrons actually, that's why you have the index E in here. They come actually in 3 flavors. They come in the type that is coming from this kind of beta decay. There is another type that is actually involving another particle that is like the electron called the mu1. And there is a third type actually that is involving the tau particle. So there are 3 flavors of them. And although the nuclear reactions involve only this type, but they have a small mass and they oscillate between all of this different flavors. As a matter of fact, these oscillations go back and forth. So yes, the neutron of the type electron actually is created, but then at the end, it keeps on hopping between one and the other. So by the time we measure this one, we are only measuring basically 1/3 of them, because the other 2/3 have been consumed by from the original quantity into the other 2 forms. So that explains perfectly everything, and the model is correct. So this is what's going on inside the sun. So this is some of the nuclear reactions that are going inside the sun. Now, the other type of nuclear reactions, if you guys look at the curve that we discussed before, way back, you have other types of fusion also that involves, so this is one fusion. This is in the beginning of this discussion that we started last time on this curve in here. So we're talking about the fusion of lighter elements getting into more and more stable configurations. The other type of nuclear reactions involve fission, actually. And fission is that when you have a heavy element, again, we were describing it. So this is really unstable itself. So if you hit it with the proper neutrons, then in this case, they can break. First of all, the elements themselves, they can break naturally in a natural process. But then you can help it. You can actually trigger that. So the atom becomes unstable and then it splits into. And that too, according to that curve, will also release energy. So that too also is a process that can release energy. So in other words, if I have 2 elements in here that are coming into the nuclear reaction, and I end up with 2 elements that are coming into the coming out of the nuclear reaction, my question is how much energy I'm going to get, really. So that's the energy, the question that we need to understand. Well, the energy in this case is just basically the difference in masses, the mass of A plus the mass of B minus the mass of C minus the mass of D times C squared, and that is how much energy in this case. Well, this number could be positive, this number could be negative. That's basically the bottom line in any nuclear reaction. Obviously, you would want to make this one as much as possible positive, so that you end up with the energy that is possible. But you could go in the opposite direction. You don't have to go in the direction that is stated. In other words, where is the? You could be going in this way on this side, and if you do that, then in this case the delta E is going to be negative. So you really need to add energy to the process to make it happen. Or you could go this way, and in this case, you're going to end up with an energy. So A and B are picked up from in a region so that you're moving this way. The same thing in here. You could be moving in the opposite direction, in which case delta E is actually negative. In this case, you really have to supply energy for it to happen. So this is basically the idea behind it. And so again, you would be given some problems where you actually do these calculations and determine if the nuclear reaction is endoenergic or exoenergic. I know it doesn't sound too good, but I think the word is better to be using the word from chemistry, which is endothermic. and exothermic. Sometimes it's used, although we're talking about energy in this case. We're not talking about thermal energy like they do in chemistry, but the words are used also, depending on how delta E will turn out to be from this process. So again, you could have fission, you can have fusion, and both of them are possible. In terms of another process that I didn't discuss in there, I discussed the PP process, the PP chain. There is another, the proton-proton chain. There is another process also that happens in the stars. That was also proposed by the German Hans, Bethe, I think. That involves carbon, nitrogen, and oxygen, called the CNO cycle. That too, actually, for stars that are about 1.3 solar masses. As these stars are big, they have more hydrogen inside their core. So they start to fuse these elements and actually fuse them all the way to carbon. Once you reach carbon, you start to go through a cycle basically of, from carbon, you make nitrogen, and nitrogen decays back to carbon. Carbon, now the new higher isotope of carbon actually with the beta decay now will involve the formation of, with the capture of, the carbon actually has to capture hydrogen, and that the net equation at the end is, at the end you will find what that 4 protons actually combine to make a helium. But again, you go through the carbon, the nitrogen by capturing a proton, then the nitrogen goes through a beta decay and change its nature back to carbon of a different isotope, and the carbon now captures another one and goes to another nitrogen. Now this is the more stable nitrogen, and the nitrogen now will capture another proton and goes to an oxygen, and the oxygen process until at the end of the cycle you are going to get into the I think this is one of the problems, and the details of it you can go through it and you can calculate the energies and everything else. So in the CNO cycle, this is not what's happening in the sun. It's actually the PP chain that is happening in the sun and the smaller stars. But this one actually accentuates, helps the bigger stars to consume more of their own proton, which they're already doing because they already have higher temperatures, even through the PP chain. So they go through their mass very quickly. Okay, in terms of applications, we have 2 applications for the fission. Unfortunately, one of them is an application. Okay, we make energy out of them, and this is in nuclear reactors. Okay, we started actually with uranium-35 and basically adding to it the neutrons, and in a controlled fashion, basically. And then at the end of the day, you end up with plutonium, and plutonium actually can be used as now a source of energy actually now, so you can use even better, more efficient ways of producing energy. This is one of them. The other application is actually in bombs, okay? Explosions. Again, this one has to do with what is known as a chain reaction. Again, you start with uranium-235, and you add to it a slow-moving neutron. Usually, you will end up with 2 products, and which ones, it doesn't matter. They're about half the atomic mass, okay? Anyway, you will end up with a 3 or 2.5 neutrons. In other words, some processes will give you 3, some processes will give you 2. On average, it's about 2.5 neutrons, plus energy, of course. Okay. Here is the thing. If you have a neutron, if you have uranium-235 in here, and you end up with about 3 protons, 3 neutrons in here, then potentially you could trigger 3 more nuclear reactions with the next door neighbor, uranium-235. Each and every one of them will produce 3. And each one of them can potentially produce 3 of its own. So you see the number in here can increase drastically, very quickly, in what is known as a chain reaction. By the way, the proton-proton chain is called a chain, but it's really not a chain. It's just a because this is what we really mean by chain reaction. The thing with it is, if this reaction is not controlled, then it could lead quickly to an out of control nuclear reaction, and that is a problem. But that out of control nuclear reaction depends on something called the critical mass. In order to achieve the critical mass, the density has to be close enough, basically. They have to be dense enough from each other so that this nuclear reaction happen. If they are far apart, then this is the neutrons basically go uncaptured, and this whole thing is not going to happen. So you really have to have a critical mass for you to do this application. Now, in nuclear reactors, you have rods that are capable of capturing the neutrons. If you push them all the way through, they will capture all the neutrons and it will kill the nuclear reactor. So basically, it will shut it down. But if you pull them just enough, the energy starts to increase because you have more and more neutrons basically released and causing more nuclear reactions. So you control it with actually rods that capture the neutrons. And in that case, basically, remember the neutrons have actually a very small penetration depth. So a lot of materials can be used to slow the neutrons. Anyway, the point being in here, you have control rod. In a nuclear explosion, though, you don't want rods in there. You want them to be in a critical mass and basically let it go. So in that case, you achieve your goal. This is one way. The other process that I was describing actually is the fusion. This is another one. So this is the normal atomic bomb. The one that was basically used against Hiroshima and Nagasaki. Now, the other one is actually the fusion. At this point, we discussed it in the stars because we know it happens in there and we have proofs for it. In terms of industry, we are still in research stage. Okay, and the biggest problem is how can you confine ionized protons? I mean, you have to have them ionized to begin with. So you have to increase their temperature. So they have very high temperature, and a gas that has a high temperature has big pressure. So you really need to push them closer from one another. That's one problem. The other problem is electrostatically also they have charges. So they don't want to be next to one another. Not only the temperature, but also in terms of charge also. So they don't really want to be next to one another. So really the biggest problem in here, how can you push them together? Confinement of this is called the plasma state, by the way. Confinement of plasma. How can you do it? There are basically two proposed methods in this case. One of them uses magnetic fields because these are charged particles. So you direct them with magnetism. And the other approach is to use lasers. Okay, and both research at this point is very hard. And the problem is you start with the protons and you try to bring the protons closer from one another. Here is another trick, though, that is actually gaining a lot of interest. If you start with helium-3 instead, all of the steps are shortcut to you. So all you have to do is get 2 helium-3 and you're in business. Or if you start with at least deuterium, you can potentially get yourself very close from the objective. So there is a big interest in helium-3 now because it's a stable element. And if you find it and ionize it, you could do the whole process a lot faster. So that is actually one of the things. Helium-3 is an extremely rare element in the Earth because of the fact that Earth does not even have a lot of helium. As a matter of fact, the first time helium was discovered was in the sun, part of the spectral analysis for the sun. And that's why it was called helium, because Helios refers to the sun. It's the gas of the sun. So that was one of the issues. So now we know helium exists, but for the vast majority, it's helium-4. So it's useless for this one. It's actually a byproduct of this whole thing. So helium-3 is extremely rare, and it's actually the remnant of that helium that formed during the Big Bang, that formed when the universe actually formed. So if we can somehow mine it, if we can somehow find it, we're in good business. Now, helium-3 in the universe, the rest of the universe, outside of the Earth, is abundant. There's a lot of it. So if somehow we can bring it in, we're in good shape. As a matter of fact, one of the sources for it is the sun, is the moon, because there is a lot of trapped helium in that. Not a lot, but that's relatively speaking compared to the Earth, a lot. that if we mine it, then we should be probably in good shape to doing fusion, because fusion does not produce a lot of radioactive materials, unlike fission is really far more energy efficient and should be, I mean, tremendous amount of energy versus the fission. Okay, from the curve you could tell also that you can produce far more energy through that process. Now, again, unfortunately, there is a third application for fusion that we succeeded in it, and that is also explosions. So in a nuclear head, what you have, so this is the head. We have actually a traditional A-bomb. Which is really the critical, not the critical, there's a high density uranium-235 in this case, or plutonium, depending on which one you use. This is usually has a traditional bomb. This is a normal, I mean, a traditional chemistry basically driven process, so that to push the element in there and get it into a critical mass. That's number one. Then you have a rod in here of hydrogen in this case that is ready to be exploded, usually of the type deuterium or triton or whatever material that is ready to go. Okay. Then you have usually a foam in here. And the surface in here is made out of beryllium. And this surface also is out of beryllium, so that it reflects all of the neutrons inside. So what's going on in this case? So when you trigger the bomb, this explosion of the chemical bomb explodes, is going to pressure the A bomb inside. And that will cause it to increase its density. And it increases its density. Now you have the neutrons flying. So now you have the A bomb that triggers. And that will immediately melt all of this foam in, that increases the temperature to several, basically hundreds of millions of degrees inside. And this will exert a pressure on this one in here that confines them, and now you have the fusion that happens in here of the higher element. So you have triple bombs basically in one of them. This is the H bomb basically. Okay, that are inside. But here's the problem: you would want this to happen so fast before the shock wave leaves the A bomb in here and reach this element, because that will tear the whole thing apart. You don't want that. You want the nuclear bomb, the fusion, to start happening in an exponential fashion. That is the one that you wanted to cause the whole thing to fall apart. That is the one that is going to, that is your product. If you are in military applications, this is what you want. You don't want the A bomb, you don't want the chemical bomb. Those are basically, especially the chemical bomb has now, I mean, relatively speaking, I mean, I know disasters are this, even a small gun can cause tragedy, let alone this thing. So again, we succeeded in destroying ourselves using what we learned from this class. But that's something that we are good at as humans, okay, unfortunately. Anyway, this is basically concludes this chapter. I think I went a little bit more in detail in it than probably I was planning on. Okay. Let's introduce chapter, and I think we talked a lot about some of the ideas from chapter 44. We still have about, oh man, about 7 minutes. Okay, it's 9:20. We're going to take a 15-minute break, and we come back to introduce chapter 44 and the ideas behind it. And we jump right into the leptons, because we started talking about them. And then, or maybe no, we start with the forces of nature, and each one of them, the associated particles with it, the bosons that are associated with it. And then we may have to get into the fermions, or the leptons, and then we'll leave the rest to next week. Sounds good, everybody? Are you guys awake?
Yes, barely.
Okay. Okay, so let me pause the recording and I will turn off the camera and mute the sound. And I will see you around 9:35. Make sense?
Yep.
Right. Again, welcome to the second part. Before we took the break, there was a question. I think it was a good question, and I thought that I should share it with the rest of the class too, because it has to do with this exams and how they are counted. Obviously, I have the 3 exams plus the final, and they are all bunched together. So yes, to answer the question, the lowest grade of one of these 4 will be dropped. So that's basically how it works. And I think you already have seen it from exam 2, that the lowest grade has been dropped, and that's the only one that is going to be dropped. So whichever one ends up to be out of the 4 is the one that's going to be dropped. Okay.
Including the final.
Including the final. Yeah, the final is actually counted with the same things as the other 3 exams. Okay. I just looked it up, and that's basically what it says in there. We're going to stick with that. Okay. So before I jump into the lab, and I'm hoping that the lab should not spend a lot of time on it. Before we jump into the lab, let's talk about the forces in nature. So let me pull my notes in here. Let me jump to chapter 44, and let me share the screen. So again, the forces in nature, they appear to be from strong to weakest, strongest to weakest. So we have the nuclear force, the strong nuclear force. We have the electromagnetic force. This is the one that is you guys have seen from physics 2. This is the one that we discovered now, and we're going to get into more details a little bit about it. It's kind of we really don't have a mathematical expression similar to Coulomb's force, for example. Okay, but we can find its values using basically measurements and using also perturbation theory. Okay, models and coming up with them. Then we have the weak nuclear force. So both of them are happening in the nucleus. They are called nuclear forces, but the weak is actually weaker than the electromagnetic force. And then way behind, you have the force of gravity. These are the 4 forces of nature. Okay. Again, in terms of strength, this is number 1, this is number 2, this is number 3, and this is number 4. Okay. How strong it is, you're asking? We're going to take this one as 1 unit. So we're going to compare everything to the strong nuclear force. This is about 1/137, which is basically alpha value. If you guys remember from the coupling constant alpha, this is really what that is. So it's really the ratio of the strong nuclear force or the weak nuclear force over the strong nuclear force. So that is gauged by that. Now, this one is of the order of 10 to the -9 as compared to this one. So it's 10 to the -7, about 10 million times weaker than the electromagnetic force, or 1 billion times weaker than the strong nuclear force. Coming down, for the gravity, remember the masses are unless you really have big masses, you really don't have a lot of gravity between them. The biggest factor is that G, if you guys remember from physics 1, which is 10 to the -11 in it. Okay, this one has a kappa, Ke, which is 1/4πε0, which has a 10 to the power 9 in it. So that is the gauging factor to begin with. Okay. In addition to the fact that you already have the masses, as I was saying, the masses are of the order of, I mean, if you just compare to this law, to the electromagnetic force, it's about 10 to the -36, okay? because the charges usually have 1 coulomb and 1 coulomb. They come in into a much bigger number than the other one, than the ratio of the masses in here. Anyway, if you do the math, it's about 10 to the negative 38 or something. I'm just 10 to the negative 40. So this one is an extremely weak force compared to the other two, the other three, okay? There was some models trying to explain why the gravity is so weak. One of them is, at least in superstring theory and string theories, they believe that the gravity is a force that leaks across dimensions, and the others they are actually linked to our universe, basically the way it is right now. Anyway, so this is one of them. So again, in here in terms of strength, I'm going to follow basically the table. This is from table 44.1. In terms of range, and we talked a lot about this one, this is of the order of a femtometer. This one can have any range you like. It's acting all the time, okay? So it has an infinite. This one also is an infinite. Remember, it depends, both of them, they depend, the potential depends on 1 over r. And the force depends on 1 over r squared. This one has even a shorter range, 10 to the negative 18 meters, or a thousandth of a femtometer. Okay, so this one has a very short range. Basically, you're talking about distances smaller than that of the proton or a neutron where they happen. Okay, and then we give them names. This is called the gluon. So the particle name now associated with this interaction. So this is the gluon. We saw this one being the photon. This one is the one that is the W plus or minus, or the Z bosons. This one, they gave it a name, the last one, but it's a hypothetical particle right now. We don't know if it really exists. There is no experimental evidence for it. Okay, it's called the graviton, but the graviton is a hypothetical particle that there is no real experimental evidence for it that it really exists, but it's a hypothetical. But the other particles, they all exist. We discovered them, the photoelectric effect, the Compton scattering, the gluon from the nuclear interaction. So they were actually detected. Also, the W plus or minus and the Z bosons also were discovered. As a matter of fact, they're extremely heavy. In terms of masses, though, mass, which is an important property, all of this have zero mass, with the exception of the W bosons, and they range in value anywhere between 80 to 91. So the first two are 80.4, and the other one is 91.2 mega electron volt. So the Z boson, the neutral one, is actually has more mass. I'm sorry, giga, not mega. So it's extremely heavier. Much more massive than the protons themselves. You're wondering for right now, how in the world is this going to explain the beta decay? Because the beta decay and all of the radioactive decay is actually, the beta decay is associated with these particles. And we have to answer that question. Because in the beta decay, for example, you have a neutron converting into a proton, plus an electron, and none of them have anywhere near this masses. But they exchange this extremely massive particles. And the trick with it is, they do it in such a way that this exchange happens so short-lived. Because, what did I do? Control Z, whatever I did. Okay. Oh, I jumped to somewhere else. Sorry. Anyway, this happens so short-lived because of the fact that delta E times delta T is greater than or equal to h bar over 2. So yes, we're talking about energy is extremely high, but if this number is extremely small, then you can still satisfy this condition. okay, we can still satisfy this condition. So this is the Heisenberg uncertainty principle. So that's really a telltale of that. Now, in terms of charges, electric charges, they're all neutral with the exception of the W plus and minus particles. So these are the force carriers. This is their carriers. In here, this whole thing starts from here. This is the force carriers. This is the range of the force. This is the strength of the force. This is the force carriers. Okay, for the gluon, it has no charge. For the photon, it has no charge. For the graviton, it has no charge. For the Z boson, it has no charge. But for the W plus or minus, it has a positive or minus 1.6 times 10 to the negative 19 coulombs. So those are charged particles, okay? In terms of spin, they're all bosons. These are all spin 1 particle with the exception of the graviton, which is a spin 2 particle. So they're all bosons. And that is important because then you can, because their wave function are symmetric, you can have as many of them as you want in the same quantum state. So there are no restrictions of the fermions where you can only have 1 particle per quantum state, basically. That includes the spin at the end of the day. So at the end, you can only have 1 particle from the fermions, but in here, you can pile them all. And that explains the BCS, basically theory that explains the superconductivity, because at that point, the electron and electron pair together to form a boson, in which case all of them, they can exist in the ground state and you don't have a problem. Another element of another thing, side note basically about the bosons is helium-4. Helium-4 is actually a boson too, because it has inside the nucleus basically 2 protons and 2 neutrons, and both of them are in the lowest energy levels in terms of the main quantum numbers, but also they have opposite spins, which means they cancel each spins. At the end, they have no spin in the nucleus. And so the outer shell too. The outer shell has 2 electrons. They are existing in the one state, and both of them have opposite spins, in which case the whole helium-4 is actually a boson, which means that if I bring its temperature very low enough, that all of the helium can exist in the same ground state and can behave like a single particle with only one wave function, because all of them, they interact constructively for that ground state and give you a macroscopic, a picture you can take of that ground state. That confirms quantum mechanics, actually. And bosons have very interesting property. This is called the superfluid, that it can actually climb through the walls of the container. So if you put the fluid inside the container, it's not like water stays in the container. This actually can, because of its wave properties, can find itself climbing the wall and ending up outside of the container. Okay, so that's basically some of the behaviors for this one. So these are the charge carriers, with the exception of the graviton and all of these properties in here that are hypothetical properties at this point, or at least model-driven properties, we don't have in it because of the fact that, as I was saying, gravity in here is super weak compared to the other forces, okay? Even this one, it took a long time for us to find the different particles in it because of the extreme weakness. As a matter of fact, the way that this thing has to be discovered is backward in here. In terms of the energies, this does not require a lot of energy to be discovered, so we dealt with it from day one. Then the next one came this one. This requires the next energy level that we dealt with. This one, in order to uncover it, we have to go to these distances. And we discovered those ones too, and we dealt with it. So, and this one in here also, we can find the gluons. This brings me to an important point down the road when we talk about cosmology, into these forces and how they broke up from each other. This force broke up the first because of its weak nature, and this stayed glued together until later on in time when the strong force split itself from this two, and this two lasted for a long time before they split in what is known as an electroweak force. Electroweak force actually was, we were able to make the conditions for it in the nuclear accelerator just enough to see that it's true. So these forces at extreme high temperatures, they combine in what is known as an electroweak weak force. Okay, one force basically. So at the end, we would be down to 3. Okay, then the standard force, if you want to call it that way, will combine all of these forces at extremely high temperatures, at least the model predicts to. So this will become just one force. At the end of the day, we will have one force. At this point, we really don't have a theory that can combine this force at extremely high temperatures with the force of gravity. But if we somehow can manage, I mean, we think at this point that the two big forces, the standard one coming from the standard model and force of gravity, at some point, they were one force, one mega force, if you wish, okay? The only force that was. At that point, at extremely high temperatures, that is just before a certain time in the early history of the universe, there was only one force that split in two, and then the one of the two that split further, and so on and so forth. Okay, so this is basically the approach that we're doing right now in terms of the forces and how that impacts the at least the forces and the ranges and things like that, and what we know up to this point in here. We're going to get into this point later on to explain the weak interactions and what's going on with those. Okay, in terms of leptons, leptons includes a whole class of particles, namely an electron, mu1. So this is the electron. E, the mu1 is mu, and then you have the tau, which is the symbol for it is tau. Okay, they all have charges, just like the electron. Okay, so they have a negative charge, they have a negative charge, they have a negative charge. In terms of mass, the electron is the lightest one, followed by, so this is 0.5 mega electron volt. This is about 100 mega electron volt, just giving the order of magnitude. And this is about 2000 mega electron volt. So this is in terms of mass, it's supermassive. And I'm going to talk a little bit about the history of how the mu1 was discovered and what's believed to be a meson, because the meson was, the hypothesis for the meson was pushed by Mr. Yukawa, who thought that before the gluon was discovered, that because now we have the photon for the light, so maybe the nuclear force is driven by neutral particles that are called mesons, and that is the one that is responsible for putting the neutron and the proton next to one another inside the nucleus. So that was his hypothesis, and he gave the properties for that meson, how much mass it should have. It should have about 200 and something mega electron volts. So immediately a year later, the mu1 was discovered, but the mu1 has the wrong charge, because it should be neutral. Okay, it has the wrong charge and it has the wrong mass, and it was not fitting the bill correctly. So at the end, it was abandoned immediately, and then the hunt for the meson continued until it was discovered later. The pion was discovered in 1947. So this is just to show you how these things started to happen. So in terms of charges, this is about 2000. I'm just giving you rough numbers. And yes, I'm looking at the table, and the table you have before you is the one that is 44.2. Okay, remember these three tables: 44.1, 44.2, and 44.3. They are critical for your assignments and for your exams. So these three tables, and 44.1 also. You need them to do a lot of, because there are so many numbers in them that you will need them for them. Okay. In terms of, okay, here comes something that we have not seen before. I have three quantum numbers, Le, L mu, and L tau. Okay. The Le for the electron is 1. The LE for the mu1 is 0. The LE for the tau particle is 0. The L mu for the electron is 0. The L mu for the mu1 is 1. The L mu for the tau particle is 0. And finally, this is 0, this is 0, and this is 1. Okay? So each particle has its own lepton number. So these are the lepton numbers. Okay? So each particle is associated with its own lepton number. Now, in terms of stability, with the exception of the mu1 and the tau particle, negative ones, the rest are stable. Okay, this is one thing. This is one side of the story. For each one of these particles, leptons, it has its own neutrino lepton. So in here, you have the neutrino electron, the electron neutrino, I should say. Similarly, you have the mu1 neutrino. And finally, you have the tau neutrino. Tau neutrino. Okay, so each particle has its own associated. Again, the lepton numbers for these guys in here are exactly like this ones. So this has the same lepton numbers also for this particle, the same lepton numbers for this particle, and the same lepton numbers for this particle. Okay, in terms of masses, they're extremely small masses. Right now, we really don't have we have upper limits for them. So this is about 2 × 10⁻⁶ MeV. This is less than that number. It's not, it's an upper limit, just from the fluctuations that we saw in terms of masses, and those experiments involve the radioactivity. Okay, we know that this is 0.19 mega electron volts, less than that number, and finally this one is less than about 18.2 mega electron volts. Okay, here is another pattern that you can see. The version of this leptons that is dominant, that we see on a regular basis in nature, is less massive than the ones that are not common. The mu1 is a particle that exists actually in the laboratory right now on its own. It exists in nature. And how does it exist? It's because of the cosmic radiation that hits the atmosphere, and that actually creates muons. And those muons, after they get created, they rain down on the Earth, and some of them have high enough velocities that they have relativistic velocity, and they make it all the way to the ground. Remember, their lifetime is about 2.2 microseconds. So if it were not for relativistic effects, they would not make it to the ground, because even if they're traveling with the speed of light c, which is 300,000 kilometers, times 2.2, 2.2 10⁻⁶ is 0.6. They travel about 600 meters. Yet we find them in the laboratory. And what's going on in this case is the distance they travel is actually, for them, the way that they see it in this case is, first of all, from our perspective, from the lab perspective, the time is not 2.2 microseconds. Their proper time is 2.2 microseconds, but when we do the calculations, when we see it ourselves, we have the time dilation. So we have to multiply that by the gamma factor. So they have lived more than 2.2 microseconds in the laboratory. In their own frame, they have lived only 2.2 microseconds. So for us, they lived long enough to travel that 10 or 15 kilometers where they were made all the way to the ground into the laboratory where they were discovered. From their vantage point, no, they lived only 2.2 microseconds. So how in the world you're telling me that I lived longer than 2.2 microseconds? That is one problem. And from their vantage point, there is length contraction. So for them, they see that entire 10 or 15 kilometers, less than 600 meters. So they lived long enough to travel that distance. Again, relativity solves this paradox. And we have the muons actually are confirmation for a lot of things because we can detect them. They have a lot of things. Confirmation for relativity first, and a confirmation for this whole thing that we're talking about. Okay. Again, so these are some of the stuff that is related to these properties in here. The tau particles also is short-lived. And the table also gives you the derivatives of those things. It decays to what, okay? Decays to what? Because they have more mass, so they can produce lighter elements, in this case, neutrinos and electrons and so on and so forth. Now, for each and every one of these particles, so you have a total of 6 now. 1, 2, 3, 4, 5, 6. Each and every one of them has its own n-type particle for a total of 12. So you have a positron, you have the muon plus, and you have the tau plus. So what I mean by that is, in terms of charge, of course, this have a negative charge E, this is negative E, negative E. In terms of charge for the entire particle is positive E, positive E, positive E. In terms of masses, it's the same mass. In terms of the lepton numbers, they're negative. So that the positron will have a negative 1, and the muon plus will have a positive 1, a negative 1, I'm sorry. And the tau plus will also have a negative 1 for its lepton numbers, L tau. Now, in terms of neutrinos, also they have their own n-type particles, and the n-type neutrino will have the same properties, the same mass, 0 charge, whatever spin for the other particle, which I didn't mention in here, which are all spin 1/2 particles. These are actually fermions. Okay, so they will have opposites of everything, especially the charge, the spin, and the lepton numbers. Okay, so that is basically in terms of a general rule. Okay, so when you look at the nuclear reaction, you need to test it, and if leptons are involved, if an electron or muon or tau particle is involved, or a neutrino for that matter is involved, you have to test you have to test the lepton numbers, you have to test the spin, you have to test the charge, you have to conservation, everything. Okay, makes sense so far? Yes. Or maybe. Okay, this is what I'm going to do. We're going to, we still have a lot of stuff to discuss on this chapter. We still have the hadrons, which are divided into mesons and baryons. And we're going to talk about the color charge in that case, okay? And the interactions using colors, in this case, chromodynamics, quantum chromodynamics, QCD. And basically after that, we're going to go through all of the conservation models. We're going to go through the eight-way model, basically, and what that means, and how that was very helpful for Mary Gell-Mann, basically to predict some particles that were not at that point, they were not discovered. So he said, okay, just like Mendeleev did with the periodic table, just go and look in there, and you're going to find a new particle, just like Mendeleev predicted new elements using his periodic table. So we're going to do that. And at the end, basically, we're going to discuss another particle that is needed actually to glue everything together, and that is the Higgs particle, in terms to give mass to everything. And that's it. Then we're going to get into cosmology, and we're going to end with that. So we're going to leave that until next week because we still have a lab to discuss. Okay, if you guys don't have any questions, I'm going to jump into the lab. So let me share with you the lab link. You find it first. Okay, share. Okay, here is the last lab that you're going to be doing in this class. It has a due date, which is May 14th, okay, by 11 p.m. And this lab has the instructions in here. There is the original lab, but please skip that. You don't have to do that because we really don't have all of the equipment. We are not in the lab to actually do this. So we're going to do a simulation instead, okay? So we're going to do the web version of this lab. And the web version has these two Excel files that you will need. So you need to have these two Excel files. And you have a lab report form that you're going to probably use to fill out this lab. Now, granted that the data that you're going to have, let me try to open this one also. Granted, the data that you will have at the end of the day will have several tables. And it will list only a handful of those tables for you. Okay. So you might need to print extra tables in here for you guys. Let me go back into the actual instructions of the lab, which I think I downloaded them in here. Yes, here they are. So the lab itself is really not that intensive in terms of work. So it goes back into the radioactivity. You're supposed to make okay, the different types of radioactivity, and it does not even talk about the gamma, the beta capture in here, but it's in there. It gives you some elements in here, carbon 14 going into nitrogen, plus in this case an electron, plus an anti-neutrino, and the same thing in here for sodium going into neon, and then you also have production of a regular neutrino and a positron in this case. So again, you're supposed to go and read through the units and answer the questions. Why does the number of protons and neutrons determine whether if an atom is stable or radioactive? What forces causes a nucleus to be unstable? What forces hold the nucleus together? Again, go back into the gamma model, okay? That explains a lot in terms of the ratio of the number of protons, the number of neutrons, and how that actually plays a role into radioactivity, and in terms of how big the atom is. And in this case, the alpha decay is most likely to bring it down into a more stable configuration. So you can answer those. These are the different types of forces that are involved with different types of decays. Again, as I was saying, the beta decay has to do with the weak force. The alpha particle is actually, in this case, has to do with the entire nuclear force, the strong nuclear force. And the proton emission is another process that we didn't talk a lot into the radioactive decay, but that's actually one of the processes. This is actually how Mr. Rutherford believed that the proton is actually the building block of all of the nuclei. Okay, obviously, the neutron was not known then, until later on it was discovered with its own properties too, okay? So the combination of the two, you could have spontaneous emission in this case. That is also involves nuclear force, and in this case, you have a number of helium atoms that depends on what elements you form in here. The weak force, we discussed it. These are the three types. I discussed even the inverse beta decay, which is basically just taking the neutrino on the opposite side, okay? This one involves just basically transition from an excited state to a lower state, usually involving, in this case, just rearrangement of the protons to bring them closer from one another because they were far away and the atom was not stable in that case. It was actually unstable due to the electrostatic repulsion. Okay, so actually the combination of both the EM force and the nuclear force. And so is this one, as a matter of fact. This one also has the the electrostatic force involved. So the details usually are a little bit more complicated than the simplistic picture in here. Again, you're calculating the energy and how often this probabilities are. In this case, you're supposed to go through the half-life and do some simple calculations. These are very easy. If you guys have difficulty with that, please let me know, okay? You're just supposed to go through these questions and answer them. And again, you can model the decay fraction of versus half-lives, how many fractions you have left after 2 half-lives, 4 half-lives, and so on and so forth. And you can take the number of half-lives and the fractions and also plot them. So this is the theoretical model. Which brings me to the lab, the actual simulation. So you have to have several dice, and you're supposed to several die, plural of dice, so that you roll them, and you roll them 20 times. So you start with the number of dice is 100 that are still. So basically, you have 100 of them, and you throw them. Anytime one of them comes up with a face of 1, you remove that. That one's radioactive. So because when we were talking about radioactivity, we said the radioactivity is actually a statistical phenomenon, meaning if I have a single atom, I don't know if it's really going to be, or a single nucleus, I don't know if it's going to go radioactive or not, because it's a probabilistic thing. So I have to wait, and I may have to wait longer than the half-life for it to go radioactive, or less than the half-life for it to go to radioactive. So it's a probability. So in this case, what we're doing in here, we're bringing 100 die, so many of them, and we're going to throw them. And we're saying in here, anytime a face value comes up to be 1, we say that nucleus went radioactive. So it's no longer part of the material that is going to go radioactive. So it's not. We're going to model that to basically simulate the condition under which the half of them are gone. So we will have half-life. So how many rolls we're going to get half-life? So we're going to roll them about 20 times. And each time a number 1 appears, we remove it from the picture. So let me open the Excel file, and I already opened it. So you guys, when you open the Excel files, you'll see that message. So let me stop sharing and let me share with you the Excel file. So in this case, when you start with, it defaults to 5. So you will see that big message in here saying that in order to run this, you have to enable editing. Please enable editing. There is no viruses in this. It's only the scripts in here. So if I roll this one, so I'm going to go back in here. Okay, and I'm going to change the number. So I'm going to just change this to 6 again, just so. So if I do that, it does the roll automatically for me. It rolls the die, all of them, the 100 of them. So keep this number in change, leave it at 100. So what it tells me in here, 11 came out to be 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 of them. So those went radioactive. So they're going to be removed from the next throw. So it's telling me you're left with 89. So I'm going to come in here and change that number to 89. When I hit enter, it removed the 11 from my the list, and it tells me upon the second roll, you lost 14 of them because 14 atoms went, or 14 nuclei and went radioactive. So they are not part of your original count now. So they're gone because their faces came out to be 1, and you're left with 75. So that's important because, again, I'm going to come back in here, stop sharing. I'm going to share with you the screen in here. So in this case, the first roll, after I rolled it, the number removed was it what? 11. So I'm going to put 11 in here in the table. And I'm left with 89. So I'm going to change this number to 89. I'm going to put 89 in here. And then the second roll, I'm going to remove 14. So I'm left with 75. Remember, we started with 100. Now we're down to 75. We lost 25 already after 2 rolls. So 75, and we lost 14 in here. And we're going to continue this operation. So this is 2 rolls. I'm going to change this one for the third roll to make it 75. Now we lost 18. So this is roll number 3. I'm lost 18. I'm down to 57, almost midway, almost half-life, okay? I started with 100. Now I'm down to 57. This number is going to be 57. So this is the 4th roll. So if I click enter, so remember, I enter 18 in my table, and then on the other side, on the right column and left column, I enter 57 for the next roll. So 57 now, I'm down to 50. So apparently after 4 rolls, I have half-life. I'm down to 50. So I lost 50 altogether, but this roll I lost only 7. So each time you roll the dice, you lose some because they went radioactive and some remain. So now I'm going to change this number to 50. So this is roll number 5. I'm down to 44. Roll number 6. I'm down to 34. Roll number 7. I'm down to 27. Roll number 8. I'm down to 23. Roll number 9. 20. After 10 rolls, I'm down to 18. 11 rolls, 17. 12 rolls. 13 rolls. 14. 15. 16. 17. Like in this case, I had 3 times I stayed with it. I'm watching it, it did not change. So 16, 17, they're all 1-1. The thing with it is, after 17 rolls, I'm down only to 1 atom basically left. I'm watching it, okay? So 17. And then in this case, if you don't hit enter, if you don't enter the value, it's not going to change. So I'm going to do 18, still the same. 19, still the same. 20, still the same. Just for the sake of argument, just to see when it's going to go radioactive, because we're supposed to stop at 20, so this is it. But I'm going to do 21, 22, 23. So each time it's giving me a different number. Right now it's giving me 5. 24. Now it has changed to the side of 2. Okay, when we throw the dice. Okay.
Oh,
20.
I have a question.
Yes.
So for the table, like once it hits 0 and 1, you just keep putting 1 and 0s on it then instead?
At the end, listen, at the end, you're supposed to stop at 20, but I'm just testing to see when it's going to go radioactive, that's all.
Oh.
Okay, so let me share with you the screen again. Share. Remember those numbers I kept on doing in here? So I remember, I think it was 11 the first time, 89. This one went, what is it? 14 or something. Yes, 14, 75, and then some other number, something. At some point we had 57 in here, and then we had 7, lost 7. And I think we had 50 at some point, either 5 or 4. I don't remember. So at that point, but we kept on going, kept on going. So at some point in here, when we were at 16, we had 1 left. So when we threw it, there was 0 removed. 1 left, 0 removed. 1 left, 0 removed. 1 left, 0 removed. 1 left, 0 removed. So I stopped there at 1 left. We have 1 at the end of the day. But I'm just testing to see, right now we're at 23 or 24, I lost count, to see when the last one is gone. So, because at some point you're asked to do it, okay? So again, I have to click on that cell and hit enter to see when it's gone. It gave me a face of 3, so it's still good. So 1, still not there, it's still there. So it's still there. Still there. So it gave me a value of 6 because this is a 6-sided dice. So again, right now I'm probably at 30 or something. It's still, so at some point this should go radioactive. I don't know why it did not go radioactive, but it should. Again, it's a probabilistic, so you can't really tell. So there is actually a random function in there. Hey, now it's gone. Probably after 35 or 36 or something. Now it's gone. I have no particles now. So I have 0 particles left to go radioactive. So if I had 0, of course, I'm going to get 0. I don't have anything. All of them are gone. Okay. But that is the point in here. That determines how many sides I need to have. I could start with 5. I think it defaults to 5 and 100 throws. So now, after the first throw of all of these dice, I lost 21 of them. If it's a 5-sided die, it doesn't give you 5. It gives you 4. So it gives you 4-sided dice. It gives you the 6, I think. It gives you also the 8. These are different species of atoms, basically. That's what you're trying to do. You will notice that the 4 is actually, these numbers are more or less related to that gap in the model of the gamma, basically. Okay. So at some point, you're going to be doing 12. At some point, I don't know, was it 12? What's the instructions in here? Yeah, 12 and then 20. 20-sided dice. Okay. So you will notice the lifetime as it depends on this number, okay? As it depends on that gap. That means that the gap of the energy is a lot less now. I mean, a lot more now, okay? You're increasing the number. Again, you're supposed to do this experiment. So let me go back into the instructions, share. So I hope that you guys know how to do this. At least this part of the table, okay? This is table 2 that you're doing. Then you have table 3, table 4, table 5. So let me go back to table 2, table 3, table 4, table 5. The number of dice you're supposed to be doing in this experiment are 4, 6, 8, 10, 12, and 20. So when you open the Excel file, it's going to default to 5, and that's not what we want. We want to change that 5 immediately to 4 and start doing the experiment with 4, and then do experiment with 10 and 12 and so on and so forth. On table 3, if you do 4, what's the number at the end of 20 will be? According to the theory, it should be between negative 0.245 and 0.875. In other words, it should be 0 because it's less than 1. Because in my experiment in here, I have actually the number of dice. So that's an integer number. So it's really not a decimal number. So it really should be 0. So the experimental value could be 0, could be 1, could be 2, could be so on and so forth, okay? And then you're going to look at this number, even if it's a 1, which is very close from 0.87, I would say it agrees. Yes, it agrees. But if you find 4 or 5, hey, there is a complete discrepancy in here, okay? So this is what the expected result for 4. For the expected result for 6, it's anywhere between 1 and 4. If you find a number that is 5, that is too big. If you find a number that is 0, that is too small. So after 20 rows, if you find that this number is not anywhere between 1 and 4, then forget about it. Okay, even 1 is acceptable because 1.01 is very close from 1. Okay, then you say, I agree. This experimental results agree with the expected result, with the expected theory. When you do 8, you're expected after 20 rows to have in here, in this cell, a number between 4 and 9. Actually, 4 is somewhat acceptable. It should be between 5 and 9. Okay. I mean, there is about 40% error to get 4. So the number really should be between 5 and 9. If you find a different number other than 5 and 9, you are, I mean, between 5 and 9, 5, 6, 7, 8, and 9. That's what I meant. Okay. Not necessarily 5 and 9. 5, 8, 5, 6, 7, 8, and 9. One of those numbers, then there is an agreement. You're in good shape. Okay. If not, then the expected result, because the sample of in here that you're dealing with is only 100 basically die. If you change the number to 1,000, then this result starts to become more and more appreciable. But you have to change these numbers accordingly. Okay. Obviously, if it's 10, it's between 9 because 8.89 is very close from 9 and 15. That means any result 9, 10, 11, 12, 13, 14, and 15 are acceptable. So if you find any different number, like 16 or 20 or like 4 or 5, this is do not agree, no, okay? And then 12 between 13.7, and you cannot tell me 13. 13 is not acceptable. 8 is not acceptable in here. So it has to be 14, 15, 16, 17, 18, 19, 20, and 21 for this case. Any one of them that you find in your result, you're in good shape. You agree. If not, you don't agree. 20, it's between 31 and 40. Because 31.1 is close from 31, enough to include it, okay? And 40 is basically the upper limit. So anyone 30, 31, 32, all the way to 40, they're good. Does this make sense to you guys?
Yep, seems pretty easy.
Okay. And for this table in here, so in here, when are you going to run out of dice, basically? Remember what I did earlier? I kept going. I kept on going around 30 something for 6. So the answer was anywhere between 21 and 36, you're supposed to run out of dice. And sure enough, I think I ran just around that number, around 35 or something. So you're supposed to continue with your experiment until you have 0. Okay? After the 20, in this case, in any case, you're supposed to continue. For the case of a 4-sided die, then in this case, you're going to end up with nothing after 13 basically trials on average, okay? So anywhere in here, you should be seeing zeros. That's what I meant by the table in here is only for one of them, but you really need to include it for all of the others, okay?
Wait, so we do? We do need to go past 20.
Yeah, you need to have the data for the others too to answer these questions. You need them, okay? To answer this question, because you need to exceed, first of all, you need to exceed all of the results, and you need to keep the tab of this data for all of the results to answer this ones in here. And again, you're supposed to tell me if there's an agreement between the theory and your results, okay? You can estimate the half-life by finding, so the half-life for 4 should be between 2 and 2.67, meaning around 2, you should be down to 50%. Here, for 4 dice. For a 6, it's anywhere between 1 and 4. I think we got it around 4. We're down to about 50. Okay. For a where am I? For an 8, it should be between 4 and 5 or 6. Okay, and so on and so forth. You guys also see you start with 100 and note where you want to about halfway. So that should explain all of the stuff that is related to radioactivity in this case, and I'm hoping that you guys will not have difficulty. There is graphs also that you're supposed to include, and let me share with you the other Excel file that you copy the data. Let me share. And it tells you which data you have to use. This Excel file, so the other Excel file. So again, we're going to start with 100. And as you plug in the numbers in here, we were at 18. No, we lost 11, and we lost 14. That's the numbers that we started with. I don't know how much we lost after that. Okay. So I know at the end we did not really get into here, but we started actually with a different number. We started with the 6 actually. Okay. And so 20th roll, we were down to 10. It's telling me it's 10 in here, but I know it's not correct. Okay, I think this is not the data that we have in there. So in other words, get your data in there. Okay, and as you get it, you're going to get those graphs that I was talking about for you, and where the theory is and where the model is. Obviously, this data in here that I have right now is not correct, because the number of dice is different than the actual data. But if you plug in the data, you will have a very beautiful match between theory and experiment. And the other one, the linear graph that you're supposed to have with the log, so you should have that. Ignore this analysis in here, it's just helping the calculations. Okay, you should also include this Excel files to represent your data. Sounds good, everybody?
Wait, for the graph, we're supposed to, I'm sorry, I missed a little bit. We're supposed to have like multiple of the different ones.
Okay, look at the instructions. And it's been a long time since I didn't do this lab exactly. All 6, yes. If you look at the, let me share. Yeah, I think that's required. You have to have all 6 of them. Let me share. All 6 graphs include all 6 graphs of all of these types. Okay. Somebody is speaking, Natasha, your voice is, were you saying something? I can't hear you. You can type it. Okay, very good. Okay, since you typed it, I got the message, okay?
So include all 6 graphs. Thanks.
Okay. Okay, I don't know if you're saying something different than what you typed, but if you typed it, that sounds good. Okay. For some reason, the sound was kind of breaking. Okay, anybody else? If not, I'll see you guys Tuesday, where we continue the discussion on chapter 44. We're going to delve in more details in there. And we're going to meet on Thursday again. I think we'll finish the chapter by Thursday of next week. And then we get into the applications. And I don't know if Canvas will be reminding you again of meetings, but there should be another important meeting, at least after that, related to the exam reviews and preparing for this coming exam and making sure that we have all of our bases covered, because then we're running it very close from the finals and the exams week and all of that. So potentially, at least we have 2 more meetings, potentially 3. And if we need to, we have still room for another one, okay? So we can meet and finalize everything and we have everything else done. Okay, sounds good, everybody? Okay, very good. Okay, so I'm going to stop the recording and then stop the whole thing. And I will see you guys next week. Thank you.